300,000 kilometers per second is the speed at which light crosses the entire circumference of the Earth 7.5 times in a single blink. And yet, if you had that speed right now, you still could not reach 94% of everything visible in the night sky. Not in a lifetime, not in a trillion lifetimes. That gap between the fastest thing possible and the actual size of the universe is what tonight is about. If this is your first time here, consider subscribing a lot to us and genuinely help support what we do. 300,000 kilometers per second. The time it takes to blink once light has already wrapped around the entire circumference of the Earth 7.5 times. 7.5 full laps around a planet 40,000 kilometers wide. In a single blink, for most of human history, light was assumed to be instant. Open a door, sunlight floods in, no delay, no travel time, just immediate presence. At the scale of a room, a city, even a continent, light does arrive instantaneously, as far as any human sense can detect. The gap between emission and reception is too small to measure without extraordinary instruments. But light is not instant. It has a speed, and that speed is the single most important number in determining what the universe will and will not allow you to do. The universe has one rule written into its deepest structure. Nothing carrying mass can ever reach 300,000 kilometers per second. Not a spacecraft. Not a particle accelerator's most energetic proton. Not anything. The closer you push a massive object toward light speed, the more energy it takes to accelerate further. Not linearly more, but exponentially more. At the final threshold, the energy required becomes infinite. The entire energy output of the observable universe poured into a single object, and it still would not cross that line. This speed is not a record waiting to be broken. It is a wall with no other side. Light gets through because it weighs nothing. A photon, one particle of light, has exactly zero mass. And because it has no mass, the universe places zero resistance on it. It moves, always, from the moment it is created to the moment it is absorbed at exactly 300,000 kilometers per second. Whether it left a candle flame 1 meter away or a galaxy 13 billion light-years distant. In early 2026, a research team pointed instruments at gamma-ray bursts, some of the most violent explosions in the universe, events that release more energy in a single second than our sun will produce across its entire 10 billion-year lifespan. The question was precise: do photons of different energies travel at even fractionally different speeds? If Einstein was wrong by even a tiny margin, that difference would accumulate across billions of light-years into a measurable arrival gap. They found nothing. Every photon arrived together. The speed of light has now been tested against the most extreme phenomena the universe produces, and it has not moved a single fraction. 300,000 kilometers per second is not a speed we measured and chose to respect. It is a speed the universe enforces on everything, everywhere, always. Against that backdrop, the solar system feels almost intimate. The moon sits 384,000 kilometers away. Light crosses that in 1.3 seconds, roughly the time it takes to say one Mississippi. During the Apollo missions, when astronauts on the lunar surface spoke with mission control in Houston, every exchange carried an audible pause before responses came back. 600 million people watching live on television heard it. That pause was not hesitation or technical lag. It was physics. 1.3 seconds out, 1.3 seconds back, 2.6 seconds round trip at the fastest speed anything in the universe can travel. Mars sits between 54 million and 401 million kilometers away, depending on orbital position. At closest approach, light takes about 3 minutes. At furthest, over 22 minutes. This gap is why every Mars rover ever built operates autonomously for large stretches of its mission. A minimum round-trip signal time of 6 minutes means real-time control is physically impossible. The speed of light does not permit it. No engineering upgrade will change this. Pluto 5.5 light hours. The New Horizons spacecraft launched in 2006 flew for 9 years, and when it finally reached Pluto in July 2015, the confirmation signal took 4 hours and 25 minutes to travel back to Earth at the W speed of light. 9 years of continuous flight. And the news of arrival still needed most of an afternoon to come home, to exit the solar system entirely past the heliopause. The boundary where the sun's influence fades into interstellar spacelight needs roughly a day and a half. 1 day and a half to cross every planet, every moon, every comet cluster, every scattered rock, all the way to where the sun's solar wind finally dissolves into interstellar space. At solar system scale, 300,000 kilometers per second is extraordinary. A light-speed traveler could visit Mars, swing past Jupiter's moon Europa, with its subsurface ocean skim, Saturn's rings loop around Neptune's storms, and cross into interstellar space before a single workday ends. The entire domain of our sun fits inside a day-and-a-half bubble, and then you step outside, and the numbers change character entirely. The nearest star beyond our sun is Proxima Centauri, a small dim red dwarf, 1/7 the diameter of the sun part of the Alpha Centauri triple star system in the constellation Centaurus. It hosts at least 2 confirmed planets, one of which sits within the habitable zone where liquid water could theoretically exist. By every measure, Proxima Centauri is our closest neighbor in the cosmos. It is 4.24 light-years away. 4 years and 3 months for light, the absolute fastest thing the universe allows to travel from there to here. The Voyager 1 spacecraft launched in 1977, and now the most distant human-made object in existence travels at roughly 61,000 kilometers per hour. At that speed, it would need 73,000 years to reach Proxima Centauri, 73,000 years longer than the entire span of recorded and pre-recorded human history multiplied by approximately 7, and Proxima Centauri is the closest one. The Milky Way, the galaxy containing our sun, every star visible to the naked eye from any location on Earth, and somewhere between 200 and 400 billion stars in total, is 100,000 light-years across. A light-speed journey from one edge to the other takes 100,000 years uninterrupted at maximum speed the entire time. The Andromeda Galaxy, that faint smudge visible on a clear autumn night in the northern sky, the most distant object the unaided human eye can detect, is 2.5 million light-years away. The light entering your eyes when you look at it tonight left that galaxy before Homo sapiens existed, before Neanderthals, before the earliest upright walking members of our genus set foot on the African savanna. 2.5 million years of uninterrupted travel through the void, and it arrives at your retina as a barely perceptible glow, 300,000 kilometers per second, the fastest speed physically permitted. And at solar system scale, it looks like a superpower. But the universe was not built to solar system scale. What waits at the true dimensions of the cosmos is something that 300,000 kilometers per second was never designed to handle. And the problem when you encounter it has nothing to do with speed. Set aside every engineering obstacle, fuel, propulsion, radiation exposure, the biological limits of the human body. None of it matters. A ship that travels at exactly 300,000 kilometers per second, available to you unlimited range. Within the solar system, that ship gives you something close to omnipotence. The Moon in 1.3 seconds. Mars at closest approach in 3 minutes, roughly the time it takes to make a cup of tea. Jupiter, the largest planet in the solar system, 11 times wider than Earth, and containing more mass than all other planets combined. Reachable in roughly 35 to 50 minutes. Saturn in 1 hour and 20 minutes. Neptune in just over 4 hours. Pluto in 5.5. And then about 6 hours after departure, you cross the heliopause and you are in interstellar space. In the time it takes to watch a long film, you have crossed the entire gravitational domain of the sun. Every planet, every moon, every ring system, every comet, traversed and left behind within a single afternoon. At light speed, the solar system becomes a neighborhood you can walk end to end before dinner. Current spacecraft take 12 years to reach Neptune. New Horizons, one of the fastest probes ever launched, needed 9 years just to reach Pluto. The difference between what light speed offers and what current technology can achieve is not a factor of 2 or 10. It is a factor of millions. Light speed compresses a 12-year voyage to Neptune into 4 hours. That compression makes interplanetary civilization feel not just possible but trivial. This is where the gift feels real, and it is real within the solar system. But the first crack appears the moment you look at where the delay between seeing and receiving begins to carry meaning. The sunlight warming the surface of Earth right now left the sun 8 minutes ago. The sun you see in the sky is always 8 minutes old. If the sun were to somehow vanish at this exact moment, Earth would continue receiving its warmth and its light for 8 more minutes before anything changed. 8 minutes of light from a source that no longer exists. At solar system scale, this sounds like a curiosity. At larger scales, it becomes something that fundamentally rewrites what travel actually means. Push beyond the solar system and light speed stops being a superpower and starts revealing what it actually is, the fastest possible rate at which information, including your ship, can cross the universe. The Milky Way is 100,000 light-years across. At the speed of light crossing, it takes 100,000 years. That is not an approximation or a worst-case scenario. That is the absolute minimum transit time at maximum permitted speed. And this is where Einstein's theory of special relativity introduces something that nobody who casually thinks about space travel fully accounts for. Time does not pass at the same rate for everyone. This is not a thought experiment, not a metaphor. It is a measured, confirmed, technologically essential fact. GPS satellites orbiting Earth at roughly 14,000 kilometers per hour experience measurable time dilation. Their onboard clocks run at a slightly different rate than clocks on the ground. Without correcting for this difference every single day, GPS coordinates would drift by kilometers within hours. The navigation system in every phone in your pocket depends on engineers accounting for the fact that time runs differently depending on speed and gravity. Scale that effect to near light speeds, and it becomes something else entirely. At 95% of the speed of light, time on your ship passes at roughly 1/3 the rate of time on Earth. 10 years pass on Earth while you experience about 3. At 99% of light speed, the compression becomes more dramatic. Push to 99.999% of light speed, and every single day of your subjective experience corresponds to approximately 200 days back home. What this creates is a situation where the numbers can look deceptively manageable from the traveler's perspective and devastating from anyone else's. A traveler moving at near light speed could theoretically cross the 100,000 light-year width of the Milky Way in what feels to them like a human lifetime of roughly 70 years. The galaxy that takes light itself 100,000 years to cross, experienced in a single lifetime if you push close enough to maximum speed. You could depart Earth as a young adult and arrive at the far edge of the Milky Way, still biologically middle-aged. But 100,000 years would have passed on Earth. Every person you knew is gone, not just dead, but through thousands of generations of descendants. Every language spoken when you departed has evolved beyond recognition or vanished entirely. Every nation, every building, every cultural reference point, every technological system gone. The planet itself has changed in ways that geology would take centuries to catalogue. The sun has aged by 1% of its total lifespan. The star patterns in the night sky have shifted as individual stars moved through the galaxy on their own paths. The Andromeda galaxy has moved measurably closer to the Milky Way on the timescale of the coming collision. You step off the ship young, intact, biologically the same person who left into a future that has no connection to anything you departed from. You traveled, you arrived, and you returned to nothing, not because anything failed, but because the physics of near-light travel consumed everything you left behind. Speed solves distance. Speed near the maximum swaps the traveler's time for everyone else's. The trade is not negotiable, but there is something beyond even this. Beyond the time dilation paradox, beyond every engineering fantasy, beyond anything a fast enough ship could solve, sits a problem of a fundamentally different kind. The universe itself is moving. It is not waiting for anyone, and the way it moves makes the entire concept of catching up to it a permanent impossibility. In 1998, 2 independent teams of astronomers were measuring Type Ia supernovae, a specific category of stellar explosion, consistent enough in brightness that astronomers use them as cosmic measuring sticks. By comparing how bright these explosions appeared from Earth against how bright they should be at their known distances, the teams expected to confirm that the universe's expansion was gradually slowing down. Gravity pulls things together. A universe full of mass should be decelerating over time. Instead, they found the opposite. The distant supernovae were dimmer than expected. Not by measurement error, not by instrumental noise, but systematically, consistently dimmer, meaning they were further away than predicted. The universe was not decelerating. It was accelerating. Galaxies were not drifting apart with decreasing momentum. They were being pushed apart faster and faster by something the data required to exist, but that no one could identify. That something now carries the name dark energy. The discovery earned its researchers the Nobel Prize in Physics in 2011, and it permanently rewrote the long-term story of the cosmos. Dark energy makes up approximately 68% of everything in the universe. It is not matter. It cannot be directly detected, cannot be isolated, cannot be explained from first principles by any existing theory. What can be measured is only its effect. The space between gravitationally unbound structures is growing, and the rate of that growth is not slowing. This is not the same as galaxies moving through space like billiard balls across a table. The distinction matters enormously. When a car accelerates down a road, the car moves through space. When the universe expands, space itself is stretching, the road is getting longer, and both the car and the destination are being carried apart on it. Einstein's speed limit applies to objects moving through space. It does not apply to space itself. Space has no speed limit. Space can stretch at any rate the energy content of the universe demands, and at sufficient distances that rate exceeds 300,000 kilometers per second. The universe expands at roughly 68 kilometers per second for every megaparsec of distance, where 1 megaparsec equals about 3.26 million light-years. A galaxy 1 megaparsec away recedes at 68 kilometers per second. A galaxy 2 megaparsecs away at about 136. Keep scaling the distance upward, and at roughly 14 billion light-years, the recession velocity of space crosses 300,000 kilometers per second. Beyond that line, any photon trying to travel toward us is on a treadmill moving faster than it can walk. It makes no progress. It never arrives. In 2024 and 2025, the Dark Energy Spectroscopic Instrument DESI published results from its multi-year survey of tens of millions of galaxies and quasars. Its findings introduced something genuinely unexpected evidence that dark energy may not be a fixed constant but something that evolves over time. Some analyses suggest it was stronger in the early universe and is weakening. Other interpretations suggest the opposite. The scientific community has not reached consensus, and the debate is active. But across every model currently under consideration, one point holds: the expansion is real, it is accelerating on timescales relevant to any discussion of reachability, and there is no credible physical scenario under which it reverses, enough to change what is and is not accessible. What this means in practical terms deserves to be stated plainly. A light-speed ship pointed at a galaxy 12 billion light-years away fires its engines. Maximum velocity, 300,000 kilometers per second, sustained and continuous. The galaxy ahead is moving away, not through space, but because the space between you and it is stretching. At 12 billion light-years, that stretching is happening faster than any ship can move. The gap grows faster than the ship can close it. The destination recedes, not because the ship is inadequate, because the road is lengthening faster than any road can be traveled. There is no propulsion upgrade that solves this. No fuel source, no theoretical framework, no physics yet conceived that would allow a physical object to outpace the expansion of space itself. The constraint is not engineering, it is geometry. The destination is not just far away. The destination is accelerating away faster than the concept of motion can address. The speed of light was never the limiting factor. It was the wrong variable to worry about. The real limit is that the universe is structured so that its own expansion has already placed most of its volume permanently beyond reach, regardless of how fast anything within it can travel. And that structure creates a line, a threshold drawn across the sky that divides the observable universe into two regions that look identical from Earth but are fundamentally permanently different from each other. Two universes occupy the same space. Most people have never been told they are different things. The first is the observable universe, the sphere of space from which light has had enough time to reach Earth since the Big Bang 13.8 billion years ago. Because the universe has been expanding during all that time, the current distance to the edge of this sphere is not 13.8 billion light-years, but approximately 46 billion light-years in every sense, direction. The expansion of space during the light's journey stretched the distance between origin point and destination. Everything within that 46 billion light-year radius has sent at least one photon toward us that has successfully made the crossing. In principle, we have received some signal from all of it. The second is the reachable universe. Everything a signal sent from Earth right now could theoretically arrive at given infinite time. Its boundary sits at roughly 16 to 18 billion light-years. Beyond that line, the expansion of space moves faster than any signal can travel. Anything on the far side is permanently beyond contact. Not today, not with better technology, not with infinite patience. The accelerating expansion makes the gap unbridgeable, regardless of waiting time. Observable universe, 46 billion light-years. Reachable universe, 16 to 18 billion light-years. Between those two boundaries lies a vast shell of space, visible in every telescope ever built and unreachable from the first moment of its observation. In concrete terms, astronomers estimate approximately 2 trillion galaxies exist within the observable universe. 2 trillion more galaxies than there are seconds in 63,000 years, each containing hundreds of billions of stars, each star potentially hosting planetary systems with their own geologies and chemistries. Of those 2 trillion galaxies, roughly 6%, about 120 billion, sit within the reachable zone. 94% are already beyond reach. 1,880 billion galaxies sit in our telescopes right now. The James Webb Space Telescope photographs thousands of them in extraordinary detail. Hubble's deep field images showed them stacked behind each other across billions of light-years like lights seen from altitude over a city at night. Every single one of them is visible, and every single one of the 94% is permanently unreachable, not because of any failure of ambition or engineering, but because the geometry of an accelerating, expanding universe drew a line, and those galaxies are on the wrong side of it. This boundary is called the cosmic event horizon. It is not a physical wall you could approach or observe directly. It is a calculated threshold, the distance beyond which light emitted right now toward Earth will never arrive, regardless of how long the universe continues to exist. Currently, that threshold sits at roughly 16 to 18 billion light-years. The threshold moves outward very slowly as the universe ages, but not fast enough to ever encompass the galaxies already beyond it. The math does not work in our favor, and no amount of additional weighting changes that. What makes this genuinely strange is the visual experience from Earth. A galaxy sitting at 40 billion light-years is fully visible through a sufficiently powerful telescope. Its light is arriving, its image is forming. Everything about it looks present, but any signal sent toward it right now at light speed will never arrive. The galaxy is receding faster than light can follow. The image you receive is a ghost information that has already crossed into you from something that has become permanently inaccessible. The boundary does not announce itself. There is no visible line in the sky separating the reachable from the unreachable. The 94% look exactly like the 6%. The same spectrum of colors, the same redshifted glow, the same apparent distances on a photographic plate. The distinction is entirely mathematical and entirely absolute. One group can be reached in principle, given sufficient technology and patience. The other group cannot be reached at all by anything ever, regardless of technology, regardless of time. 2 trillion galaxies. 6% on one side of a line you cannot see, 94% on the other. And the line is moving slowly in the wrong direction right now. 160 billion stars per year cross from the reachable side of the cosmic event horizon to the unreachable side. For context, the Milky Way contains somewhere between 200 and 400 billion stars total. Every 1 to 2.5 years, a volume of stellar mass equivalent to an entire large galaxy silently crosses a line from which there is no return. Not with a flash, not with any visible sign. Just the quiet arithmetic of an expanding universe, moving the boundary by an imperceptible increment each year, compounding over billions of years, into the loss of almost everything. Most changes in the universe operate at timescales that make human civilization invisible by comparison. Stars burn for billions of years. The cosmic web of galaxy filaments takes hundreds of millions of years to shift its architecture. The very arrangement of constellations in Earth's night sky, those fixed-looking patterns of light, changes measurably only over tens of thousands of years as individual stars drift along their own paths through the galaxy. Against all of that, a human lifetime is too short to register. Against all of that, recorded human history from the first writing to today is less than a rounding error. But the contraction of the reachable universe is operating continuously on every timescale simultaneously. 160 billion stars per year is not a rate that manifests visibly on any human observable timeframe. Per century, it is 16 trillion stars still invisible. Per million years, it is 160 quadrillion stars still invisible to direct observation, detectable only through the precision measurement of how the cosmic event horizon has shifted between epochs. The loss is real and total and happening right now. It simply does not announce itself. This is what physicists call the shrinking of the Hubble volume, the region of space with which Earth can in principle exchange information. As dark energy accelerates the expansion of space, the Hubble volume shrinks relative to the total universe. Not because Earth is moving inward, because everything else is being carried outward faster than light can follow. To put numbers to it, the Hubble volume currently encompasses a sphere roughly 92 billion light-years in diameter, the full observable universe. The reachable portion of that sphere, bounded by the cosmic event horizon at 16 to 18 billion light-years, is a much smaller inner region. Every year, that inner region loses the equivalent of a large galaxy's worth of stellar mass from its outer boundary to the unreachable zone beyond. Every decade, that loss accumulates into something closer to a small galaxy cluster. Every billion years, entire superclusters, gravitational structures containing thousands of galaxies spanning hundreds of millions of light-years, will have crossed entirely beyond the reach of anything departing from here. The light arriving from receding galaxies tells the story in its own physical properties. As a galaxy moves away from us, or more precisely, as the space between us, and it stretches, the light it emits gets stretched by the same expansion. Wavelengths lengthen. Colors shift toward red, then infrared, then wavelengths too long for any conventional optical instrument to detect. The further and faster a galaxy recedes, the more extreme this redshift becomes. For galaxies near the edge of observability, light that originally left as ultraviolet arrives at Earth as infrared, stretched by billions of years of cosmic expansion during its journey. James Webb was built specifically to catch this infrared light, which is why it can observe galaxies that Hubble could only barely resolve. Edwin Hubble, working in the 1920s, first established that the faint smudges of light beyond the Milky Way were not clouds of gas within our galaxy, but independent island universes, each containing billions of stars, and that they were receding from us. Their light shifted toward the red end of the spectrum in proportion to their distance. At the time, the most distant objects he could observe were receding at speeds that looked dramatic, but remained well below the speed of light. The universe appeared to be expanding, but manageably so. The possibility that this expansion might be accelerating, that the recession velocities of the most distant objects would eventually approach and then exceed light speed, was not yet part of the picture. That picture would not arrive until 1998, and it changed everything. The mechanism of redshift that Hubble observed is the same mechanism that is currently stretching the transmissions from the 94% of galaxies already beyond the cosmic event horizon into wavelengths too faint and too long to detect. It is the same mechanism that will over billions of future years stretch the transmissions from galaxies currently still within the reachable zone into silence. The process has no off switch. It has no natural reversal under any scenario consistent with current observations. It simply continues year by year, galaxy by galaxy, photon by photon, until what was once a universe of 2 trillion galaxies becomes, for any observer who remains, a universe of 1. But there is a physical endpoint approaching that no instrument upgrade can address. At some point, a galaxy's recession velocity becomes large enough that its light is stretched to wavelengths longer than any detector can register. The galaxy does not disappear suddenly. It fades over billions of years into wavelengths so long they carry almost no energy, arriving with such low frequency that the intervals between individual photons grow longer than the age of the universe. Eventually, there are no more photons. The transmission ends, not because anything broke, because the physics of expansion finally finished the job. This process is already underway for the most distant objects currently visible. The galaxies at the edge of Webb's observational reach are already deeply redshifted, already faint, already sending light that has been traveling for over 13 billion years. Future generations of telescopes will need instruments of increasing sensitivity to catch the increasingly attenuated signals from the most remote objects, and eventually no amount of increased sensitivity will help because the photons themselves will carry too little information to be useful. The door is not slamming. It is closing the way. A tide recedes gradually, continuously, invisible day to day, and then you look at where the waterline used to be, and it is somewhere else entirely. After 1 billion more years, the reachable fraction drops from 6% to roughly 5%. After 100 billion years, the reachable universe will consist almost entirely of the galaxies gravitationally bound to our local group. The small cluster of about 50 galaxies, including the Milky Way, Andromeda, and their S-station, satellites, everything beyond that gravitational bond will have crossed the horizon. Right now, the record is still open. 2 trillion galaxies visible. The expansion of space measurable in real time across billions of light years. The Big Bang's afterglow, detectable from every direction. All of it still transmitting, still arriving. But every transmission from those 94% of galaxies is old light. It left those galaxies billions of years ago when the universe was younger and the distances were smaller. The galaxies themselves have long since moved further away, and any new light they emit now will never reach us. The images arriving tonight in our telescopes are the last transmissions from correspondents who have already permanently moved beyond any address we could send a reply to. What those transmissions contain, and what it means that they are still arriving, is something worth understanding before the window closes further. Every observation in astronomy is an act of reading the past. When you look at any object in the sky, you are not seeing it as it currently exists. You are seeing it as it was at the moment the light you are receiving departed its source. The gap between departure and observation is the travel time of light across whatever distance separates you from the object. That gap is always there. The universe does not offer real-time observation. It never has. Every image ever captured by every telescope in history, every photograph of a nebula, every spectrum of a distant quasar, every survey image of a galaxy cluster is a document from the past, not a window into the present. At human scales, this is imperceptible. Light crosses a room in about 10 nanoseconds. Even at the moon's distance, 384,000 kilometers, the delay is 1.3 seconds. Noticeable only if you are an astronaut having a conversation with mission control from the lunar surface. During the Apollo missions, every exchange between astronauts and Houston carried that audible pause in both directions. 600 million people watching live on television heard it as an awkward silence. It was not awkward. It was the speed of light doing its job across 384,000 kilometers of vacuum. At astronomical distances, the delay between emission and reception stops being a detail and becomes the entire story. The sunlight on your skin right now left the sun 8 minutes ago. The nuclear fusion reactions, generating at hydrogen atoms, colliding under pressure so extreme, they fuse into helium, releasing energy that then spends thousands of years fighting its way from the core to the surface, before finally escaping. As photons, those reactions happened 8 minutes ago from your perspective. The sun you see in the sky is always 8 minutes old. If a massive solar flare erupted at this exact moment, you would not know for 8 minutes. You would continue reading, sleeping, living normally while the event unfolded, and only then would the light carrying the news arrive. The implications compound the further out you go. Light from Jupiter, the largest planet in the solar system, takes between 32 and 52 minutes to reach Earth, depending on orbital position. The images returned by the Juno spacecraft orbiting Jupiter right now, the data being transmitted back to Earth at the speed of light, arrive with a delay between 32 and 52 minutes built in. There is no shorter path. That delay is the minimum possible at maximum permitted speed across the actual distance. When Juno's cameras fire engineers on Earth learn about it close to an hour later, Betelgeuse sits roughly 700 light-years from Earth. The light entering your eyes when you observe it tonight left that star around the year 1325 CE, during the height of the medieval warm period in Europe, roughly a century and a half before Gutenberg printed the first Bible before the Black Death had fully receded from the continent. Betelgeuse is a red supergiant nearing the end of its stellar life. One of the largest stars visible to the naked eye, so large that if it replaced our Sun, its outer atmosphere would extend past the orbit of Jupiter. It is expected to explode as a supernova at some point within the next 100,000 years, possibly far sooner. In 2019, it dimmed dramatically, dropping to about 40% of its normal brightness over several months in what became known as the Great Dimming Event. Astronomers debated whether this indicated imminent explosion or a large surface ejection. Follow-up Hubble data confirmed it was a massive plasma plume that had erupted, cooled into dust, and temporarily obscured part of the star from Earth's perspective. But throughout those months of uncertainty, one fact remained constant. Whatever was happening on Betelgeuse, it was happening 700 years ago. The event played out during the medieval period. We watched it in 2019. Betelgeuse may already have exploded. The explosion may have occurred 500 years ago, 200 years ago, last week. If it exploded last week, a column of neutrinos traveling at near light speed is already in transit toward Earth. Neutrinos travel slower than photons, but the difference is minuscule across 700 light-years, followed by the expire, full electromagnetic flash of the supernova itself. Detecting that incoming neutrino burst before the light arrives would give Earth's neutrino observatories Super Kamiokande in Japan Ice Cube at the South Pole a few hours of advance warning. Underground detectors are watching for exactly this signal. But the light from the explosion when it finally arrives will be visible in full daylight, bright enough to cast shadows present in the night sky for weeks. It will be the closest supernova in 400 years. And none of it has anything to do with what Betelgeuse is doing right now, only what it was doing 700 years ago when the light currently en route first departed. The Andromeda Galaxy, 2.5 million light-years away, appears in our sky as it was before our genus existed. The light arriving tonight left Andromeda approximately 2.5 million years ago, when early members of our lineage were making simple stone tools on the African savanna and the global climate was cooling toward the Pleistocene ice. Ages. The galaxy has continued evolving during those 2.5 million years of transit time. Stars have been born and died. The spiral arms have rotated. The supermassive black hole at its center has consumed gas and grown. The galaxy is measurably closer to us now than it appears in our telescopes because the light showing its position reflects where it was 2.5 million years ago, not where it is tonight. What appears in our telescopes is not Andromeda as it is. It is Andromeda's 2.5 million year old transmission still arriving. The Virgo cluster, a gravitationally bound collection of more than 1,300 galaxies, located about 60 million light-years away. The dominant mass concentration of the supercluster, our own local group is an outlying member, appears as it was 60 million years ago. That is the geological moment an asteroid impact ended the reign of non-avian dinosaurs on Earth. If an intelligent civilization existed somewhere in the Virgo cluster and pointed a powerful enough telescope at our planet right now, what they would see 60 million years later, when that light finally arrives, is a world dominated by massive reptiles. No mammals in ecological dominance, no language, no cities, an Earth with no indication of what would eventually emerge from it. What this creates when you assemble all the layers simultaneously is something that has no equivalent in any other field of observation. A photograph of the Virgo cluster contains 60 million year old light. The same photograph, if it captures a foreground galaxy at 30 million light-years, contains 30 million year old light right next to it. A star in our own Milky Way in the corner of the frame might contribute light from a few thousand years ago. The moon in the background of a wide-field image contributes light from 1.3 seconds ago. All of it is in the same image. All of it looks equally present. The entire history of the universe, is flattened into a single snapshot with different depths of time occupying the same plane of observation. James Webb has pushed the archive deeper than any instrument before it. In its first years of scientific operation, Webb confirmed distances to galaxies whose light left them between 300 and 500 million years after the Big Bang, when the universe was between 2 and 4% of its current age. Webb's NIRCam instrument captures near-infrared wavelengths, carrying light from those ancient galaxies stretched by billions of years of cosmic expansion from their original ultraviolet frequencies. Without infrared sensitivity, those galaxies would be completely invisible. Webb was built specifically to receive them. What Webb found challenged existing formation models. Those early galaxies are unexpectedly massive and luminous for objects so young in cosmic history. Galaxy Gienzonon, one of the most distant confirmed in Webb's dataset, contains stellar mass, roughly 1 billion times the mass of our Sun, assembled within 430 million years of the Big Bang. Standard models of galaxy formation based on how slowly dark matter halos were expected to accumulate enough mass to seed large galaxy formation did not predict objects of that size that early. Webb's observations of multiple such objects have prompted serious theoretical revision, new simulations, new estimates of early star formation efficiency, new questions about the initial conditions of the Big Bang itself. The archive is not just open, it is actively rewriting the story it contains. The cosmic microwave background takes the archive to its furthest extent. It is the oldest light in the universe, photons emitted 380,000 years after the Big Bang, when the universe cooled enough for electrons to bond with protons and form neutral hydrogen, and the cosmos became transparent for the first time. Those photons have been traveling for 13.8 billion years. They fill the sky uniformly from every direction, arriving at Earth from all sides simultaneously at a temperature of 2.725 degrees above absolute zero. They are too cold to feel at wavelengths far beyond human vision, but they are physically present, passing through the room you are in right now, arriving from every direction, carrying encoded information about the universe's state. When it was 380,000 years old, the temperature variations in the CMB fluctuations of roughly 1 part in 100,000 are the seeds from which every galaxy, every star, every planet in the observable universe eventually grew. The slight overdensities became gravitational attractors. Matter accumulated in those wells over hundreds of millions of years, building the cosmic web of filaments and voids visible in modern galaxy surveys. Everything in the observable universe, including the planet you are on, and every instrument ever built on it, traces its structural origin to the pattern encoded in photons, still arriving from every direction. Satellites, including WMAP and Planck, spent years mapping these variations with extraordinary precision. Planck's final data release characterized the state of the early universe with better than 1% precision across dozens of cosmological parameters. The CMB is the most precisely characterized dataset in all of cosmology, and it was generated by reading photons 13.8 billion years old. The night sky, understood fully, is not a window into the present. It is a layered archive of nearly the entire history of the universe, with every observation positioned at a different depth in time. The Moon from 1.3 seconds ago, Betelgeuse from 700 years ago, Andromeda from 2.5 million years ago, the Virgo cluster from 60 million years ago. The most distant galaxies Webb can observe from 13.5 billion years ago. The cosmic microwave background from 13.8 billion years ago. All of it arriving simultaneously as if contemporaneous, when in truth it is a record stretching across almost the entire age of the universe, arriving all at once from every direction into any instrument pointed at the sky. The archive is still open. Every photon currently in transit from across the observable universe is still traveling toward Earth, still carrying its encoded message. The universe is constantly delivering new communications from its own deep past, and the delivery has been continuous since the first transparent era. But the archive has an expiration. The delivery will not continue indefinitely, and what the universe looks like after the last delivery arrives and silence follows is what makes the current moment something other than ordinary. The numbers from Destination 5, 160 billion stars per year crossing the cosmic event horizon, are happening right now, invisibly, silently, as a purely mathematical consequence of dark energy, accelerating the expansion of space. No visible event. The stars do not flash or fade when they cross. 1 year, a signal sent toward them might theoretically arrive in some unimaginably distant future. The next year, the physics of the expansion have shifted just enough that it cannot. The threshold moves, the count continues. The crossing itself is not an event that happens to the stars. It is an event that happens to the relationship between those stars and us. From the perspective of any civilization existing in those distant galaxies, nothing changes at the moment their galaxy crosses our event horizon. Their stars still burn, their physics still operate, their own night skies still contain their own observable universes, their own archived light from their own cosmic histories. What changes is only this: any photon they emit after that crossing pointed toward Earth will never arrive. The relationship has been terminated not by anything either party did, but by the geometry of an expanding universe drawing a line between them. This rate of loss is not uniform across cosmic history. In the early universe, when dark energy was still a small fraction of the total energy density, overshadowed by matter and radiation, the expansion was slower and the accessible volume was growing. Civilizations that hypothetically existed billions of years ago would have observed more reachable galaxies than we observe today, not fewer. The universe was more permissive then. The window was wider, there was more out there to reach, and reaching it was less futile. The transition point, the moment when dark energy began to dominate the universe's energy budget, and the expansion began genuinely accelerating, occurred approximately 5 billion years ago. Before that point, the expansion was decelerating. Gravity was winning. After that point, dark energy won. The universe stopped slowing down and began speeding up. Everything that happened to the reachability of distant galaxies, the shrinking of the Hubble volume, the loss of 160 billion stars per year, the irreversible retreat of the accessible universe is a consequence of that. Transition playing out continuously from 5 billion years ago to today to the indefinite future. We exist on the accelerating side of that transition. We arrived cosmically late enough to find the universe already pulling away, already contracting the domain of the possible, already past its moment of maximum openness. Civilizations that might have existed 3 or 4 billion years ago, had the universe been hospitable enough to produce them that early, which it likely was not at the required sophistication, would have observed a universe with more reachable galaxies, a wider accessible sphere, a less advanced contraction. The window we have inherited is smaller than the window that once existed. Dark energy has been gaining dominance as the universe expands and the density of matter decreases. With less matter to resist it, dark energy's influence strengthens. The expansion accelerates. The event horizon, rather than growing to include more of the observable universe, shrinks relative to the total observable sphere. Every billion years, a larger fraction of what we can see becomes permanently unreachable. This dynamic has a name in the cosmological literature: the increasing isolation of the local group. The galaxies within our local group, the Milky Way, Andromeda, the Triangulum Galaxy, and about 50 smaller satellite galaxies are gravitationally bound to each other. Their mutual gravity is strong enough that the expansion of space cannot pull them apart. They will remain together, interacting, exchanging matter and energy across trillions of years. But everything beyond them, every galaxy outside the local group's gravitational domain, is on a one-way trajectory away from us, accelerating, receding, eventually crossing the horizon, and becoming permanently inaccessible. The local group itself is a small structure by cosmological standards. The Milky Way and Andromeda are its 2 dominant members. The rest are smaller satellite galaxies orbiting one or both of the main 2. The entire local group spans roughly 10 million light-years, enormous, by human reckoning trivial, against the 46 billion light-years of the observable universe. What the local group represents from the perspective of long-term cosmic accessibility is the final enclave, the small pocket of the universe, that gravity has tied together firmly enough that dark energy cannot separate it. When everything else has crossed the horizon, the local group remains. The light from galaxies approaching the horizon undergoes extreme redshift as they recede. A galaxy at the horizon's edge today emits light that by the time it reaches Earth has been stretched from its original wavelength into something barely detectable by the most sensitive instruments. Over billions of years, as that galaxy crosses further beyond the horizon, its light becomes increasingly attenuated. Longer wavelengths, lower energies, greater intervals between photons, until the last photon from that galaxy finally arrives, carrying almost nothing, and then there are no more. The galaxy is not gone. It continues to exist somewhere in the expanding universe, but its ability to communicate with us, to send any signal that could ever reach Earth, is over. The communication has permanently ended, not because we stopped listening, but because the geometry of space-time has made further contact physically impossible. One more thing worth holding: the loss of those 160 billion stars per year to the unreachable zone does not just represent the loss of potential destinations. It represents the loss of potential information. Every star system crossing the horizon contains, in principle, some record of cosmic history that will never reach us. The light emitted by its stars, the gravitational waves produced by its mergers and collisions, the neutrinos released by its texas, supernovae, all of that information generated by physical processes occurring in those systems right now and into their futures will never cross the event horizon in our direction. It will propagate outward from those stars traveling at the speed of light, and it will never reach us. We are not just losing potential places to visit. We are losing potential knowledge, the universe redacting its own record system by galaxy in real time. 160 billion stars per year. A galaxy's worth of stellar mass, silently crossing a threshold every 1 to 2 years continuously. The door has been closing since dark energy began dominating the universe's energy budget 5 billion years ago. It is closing right now, and it will keep closing long after any observer remains to notice that it has shut. Project forward 1 trillion years. A trillion years is not a number human cognition handles naturally. The universe is currently 13.8 billion years old. A trillion years is roughly 72 times that. On a timeline where the entire age of the universe so far occupies a single calendar year, a trillion years is 72 years. A full human lifespan elapsed after that year ends. Every event in cosmic history up to this moment occurs within the first 5 days of that year. Everything else is what comes after. By a trillion years from now, the sun will have long since expanded into a red giant, consumed its inner planets, scorched the Earth's surface beyond any recognition, and collapsed into a white dwarf, slowly radiating its remaining heat into the void. New generations of stars will have formed and died many times over in the Milky Way. The galaxy itself will have restructured as stellar orbits evolve over millions of years through gravitational interactions. But the most significant change, the one that defines what any observer experiences at 1 trillion years, will not be about individual stars or individual galaxies. It will be about what remains visible at all. The expansion of space, driven by dark energy and accelerating continuously, will have pushed every galaxy outside the local group beyond the cosmic event horizon billions of years earlier. Not gradually dimming, crossing the horizon, then receding faster and faster, their light stretched to wavelengths so long they carry no detectable energy. The intervals between arriving photons growing longer than the age of the universe, until by any practical definition the transmission has ended. Each galaxy goes silent, one by one, without any signal that it has happened. The cosmic microwave background, currently at 2.7 degrees above absolute zero, will have cooled to a temperature so close to absolute zero that no conceivable detector could distinguish it from nothing. Its photons, stretched by trillions of years of additional expansion, will carry energies so low they effectively cease to exist as detectable signals. The large-scale structure of the universe, the cosmic web, the galaxy filaments, the superclusters, will have expanded beyond any observational horizon, not just too dim to see, physically dispersed. The structure that took billions of years for gravity to assemble will have been pulled apart by trillions of years of accelerating expansion. The nodes that once anchored the web, now separated by distances so vast that no signal from one could reach another within the remaining accessible universe. What remains visible from any observatory within our local group at 1 trillion years will be approximately one object, the merged remnant of the Milky Way, Andromeda, and the other galaxies of the local group, a single large elliptical structure that cosmologists already call Milkomeda, floating in absolute darkness. No other galaxies detectable in any direction, no background radiation registerable by any instrument, no expansion detectable through redshift because there are no distant objects against which to measure redshift. No hint that the universe was ever anything other than this one island of stars in an infinite, featureless void. Lawrence Krauss and Glenn Starkman described the situation facing observers in the remote future with precision that has only grown more relevant as cosmological understanding has deepened. Their analysis concluded that a civilization arising in the merged remnant of the local group 1 trillion years from now would look out at a universe that appears static, singular, and eternal. They would see one galaxy. They would detect no expansion. They would find no cosmic microwave background. They would have no observational evidence accessible through any means available to them that any other galaxy has ever existed, that the universe was once filled with 2 trillion galaxies, that space is currently expanding, or that a big bang ever occurred. The 3 observational pillars of modern cosmology, the cosmic microwave background, the large-scale structure of the universe, and the measurable expansion of space through galaxy redshifts, will all be gone. Not hidden, waiting to be uncovered by more sophisticated instruments. Gone. Physically erased by the same expansion that right now distributes them across the sky for any observer willing to look. Those future astronomers working with every technique available to a civilization 1 trillion years more advanced than ours would construct a cosmology of profound simplicity. One static island universe, surrounded by infinite emptiness, apparently eternal, and they would be wrong, cosmically, fundamentally wrong about the nature of the universe, but the physical universe would give them no way to know it. The knowledge we have built, the Big Bang, cosmic expansion, dark energy, 2 trillion galaxies, the cosmic microwave background is knowledge available only because we exist at this specific point in cosmic time, not earlier when the universe was too hot and dense for complex observers, not later when the evidence will be irretrievably gone, in between, in the window. Return to the archive for a moment. Every photon currently in transit from across the observable universe is carrying something. A message from whatever source emitted it, a stellar surface, an accretion disk, a supernova remnant, the primordial plasma of the early universe, encoded in its wavelength, its energy, its polarization. The message left its source sometime in the past 1.3 seconds ago for moonlight, 8 minutes for sunlight, 4 light years, and change for the nearest star billions of years for the most distant galaxies 13.8 billion years for the cosmic microwave background. All of those messages are arriving simultaneously. All of those messages are present in the sky tonight, right now, in every direction. The universe is delivering its entire history continuously to any instrument capable of receiving it. This is astronomy's fundamental advantage over every other observational science. A geologist studying Earth's past must infer history from rock formations, indirect evidence gaps in the record, interpretive uncertainty at every step. An archaeologist reconstructing a past civilization works from fragments, rarely from complete records. An astronomer looking at the Virgo cluster is not inferring what it looked like 60 million years ago. The astronomer is receiving its direct transmission from 60 million years ago. The signal is present. The message is intact. The archive has not degraded. It has been traveling through vacuum at the speed of light, arriving exactly as it left, carrying exactly the information that was encoded when it departed. That directness, the fact that cosmic history is written in light that is still arriving, is what makes the golden age of cosmology possible, and what makes the phrase meaningful rather than merely poetic. Since the 1990s, the pace of cosmological discovery has been unlike anything in the preceding centuries of the field. The cosmic microwave background was mapped with extraordinary precision. Dark energy was discovered. Dark matter was confirmed through gravitational lensing and galaxy rotation curves. Gravitational waves ripples in spacetime predicted by Einstein in 1915, but undetected for a full century, were first observed by LIGO in 2015, opening an entirely new observational channel into the universe that carries information about events no photon can reach. James Webb began photographing the first galaxies in human history. DESI began mapping the three-dimensional structure of tens of millions of galaxies to constrain the behavior of dark energy over 10 billion years of cosmic history. The convergence of these instruments, these capabilities, and these specific questions is not inevitable. It is a coincidence of technological development within a specific window of cosmic time during which the evidence remains complete and readable. Slightly earlier in the universe's history, before the CMB had cooled to detectable wavelengths, before the large-scale structure of galaxies had assembled, many of these observations would be impossible. Slightly later, after the horizon has consumed more of the observable universe, after the CMB has cooled past detection, they will become impossible again. Every photon arriving from the 94% of galaxies, already beyond the cosmic event horizon, is a last communication from an unreachable source. Those galaxies continue to exist somewhere in the expanding universe, their stars still burning, their physics still operating, but their ability to send us anything new has ended or is ending. What arrives tonight from them is the last installment of a correspondence that the geometry of space-time has permanently terminated on their end. And yet the correspondence is still arriving. The last photons from galaxies already beyond the horizon will continue arriving for billions of years. The universe is enormous, and the rearmost photons of any galaxy's transmission are still in transit. The archive will remain partially open for an immense span of future time, even after the door to new information has closed. Distant future astronomers, not in a trillion years but in billions of years, will still receive light from galaxies that have already crossed beyond the reach of any future signal sent from Earth. They will be reading old mail from addresses that can no longer be reached, but they will still be able to read it. What disappears first is not the visibility of distant galaxies. What disappears first is the ability to interact with them, to send anything there, to influence anything there, to have any causal relationship with anything there. The observable universe shrinks from the reachable end. The archive closes from the outgoing direction. You can still receive. You can no longer send. And this asymmetry, still receiving from places that can no longer be reached, is perhaps the most precise description of what it means to be an observer in an accelerating universe. You are downstream from a past that is still transmitting. You are upstream from a future that is already cut off. The universe passed through a long period during which it was physically incompatible with complex observation. For the first 380,000 years after the Big Bang, the universe was a plasma-charged particles so energetically agitated that photons could travel only tiny distances before being absorbed and re-emitted. Nothing could see across any meaningful distance. No stars existed, no galaxies, no chemistry capable of producing observers of any kind. The universe was luminous and completely opaque simultaneously, full of energy, transmitting nothing of that energy across any useful range. Then it cooled enough for neutral atoms to form. Photons traveled freely for the first time, and over the following hundreds of millions of years, gravity pulled hydrogen into clouds, clouds into protostars, protostars into stars. The first generation of stars burned hot and fast, lived for a few million years, and exploded, seeding the universe with carbon, oxygen, nitrogen, iron, every element heavier than helium, forged in stellar cores and scattered by stellar deaths. A second generation formed from this enriched material, then a third, each generation building the chemical diversity that eventually makes rocky planets' liquid water and carbon-based chemistry possible. About 4.6 billion years ago, in a spiral arm of a galaxy in the Virgo supercluster, a cloud of third-generation stellar material collapsed into a new star with a disk of debris around it. Within 100 million years, that debris organized into planets. On the third planet, liquid water pooled on the surface. Within 1 billion years, chemistry in that water organized itself into self-replicating molecules. Within several billion years more, those molecules produced multicellular life, nervous systems, brains capable of modeling the external world with increasing precision. Those brains eventually built telescopes, and with telescopes over roughly 5 centuries of iterative improvement, from Galileo's first astronomical observations in 1609 to the deployment of James Webb in 2021, they reconstructed the history of the crescent universe. They determined that the universe is 13.8 billion years old. that it began in an event of incomprehensible density and temperature, that it is composed primarily of dark matter and dark energy, neither of which can be directly detected and neither of which is explained by any current theory, that it is expanding at an accelerating rate, that it contains approximately 2 trillion galaxies, that 94% of those galaxies are already permanently beyond reach, that the entire observable record of cosmic history is encoded in light currently in transit, arriving continuously from distances spanning the full 46 billion light-year observable sphere, and that all of this evidence, the structure, the archive, the record will eventually be erased by the same expansion that created the space for observers to exist. The phrase "golden age of cosmology" appears in peer-reviewed literature, in conference proceedings, in the opening paragraphs of grant proposals for the next generation of observational facilities. It is not a compliment. It is a technical description of a historically unusual state of information availability. The 3 pillars of modern cosmology, the cosmic microwave background, the large-scale structure of the universe, and the direct observational evidence of cosmic expansion through galaxy redshifts, are all simultaneously measurable, mutually reinforcing, and fully readable. All 3 conditions met simultaneously for the first time since complex observers became possible in a window with physical boundaries on both sides. The James Webb Space Telescope's deep field images show thousands of galaxies in a patch of sky small enough to be covered by a grain of sand held at arm's length, spanning billions of years of cosmic history stacked in depth like geological strata, each layer older and further than the last. Webb's spectroscopic data is actively revising the timeline of early galaxy formation. DESI's galaxy survey is constraining the behavior of dark energy across 10 billion years of cosmic time. The Euclid satellite is mapping galaxy positions and shapes across 15,000 square degrees of sky. The Vera Rubin Observatory has begun its decade-long survey of the southern sky, photographing the entire accessible hemisphere every few nights to build a time-lapse record of the variable universe. The Nancy Grace Roman Space Telescope will add wide-field infrared observations at a scale that individual deep fields cannot provide. All of this is converging in the same era, the same window, the same physical moment in cosmic time when the evidence is present, the observers exist, and the instruments to read one using the other have been built. 300,000 kilometers per second, the absolute maximum the universe permits anything to travel. Fast enough to reach the moon in 1.3 seconds, Mars in 3 minutes, the edge of the solar system in a day and a half, 4 years and 3 months to the nearest star, 100,000 years to cross the Milky Way, 2.5 million years to Andromeda, and 94% of the 2 trillion galaxies currently visible in the sky, permanently irreversibly by the hard geometry of an accelerating, expanding universe beyond the reach of any object or signal that could ever depart from Earth. That gap is not a failure of physics. It is not an oversight in the design of reality. It is a measurement of how large the universe is, how fast space can expand, and what those 2 facts together mean for any observer embedded within it. But the measurement was made here by observers on a rocky planet in the outer arm of an unremarkable galaxy, using instruments assembled across 5 centuries of incremental effort in a window of cosmic time that opened after the universe cooled enough for chemistry to produce complex minds, and will close when the evidence those minds depend on has been stretched past detection by the same expansion that gave them space to exist. The 2 trillion galaxies are visible tonight. The cosmic microwave background is arriving from every direction at this moment. The expansion of space is measurable in real time across billions of light-years using instruments currently in operation. The Big Bang is readable in the structure of light that has been traveling since 380,000 years after it occurred. The archive is open. That is not a small thing. Somewhere in the receiving end of all that ancient light, in the specific moment of cosmic history, when the evidence is complete, the instruments are built, and the minds to interpret them exist, is where you are.